Can we start, or we need to wait?
We can start.
Yeah, probably we can start, but Nikolay, could you please introduce yourself for people who don't know?
Sure. Good afternoon, dear colleagues. I'm Nikolay Koshev. I'm an assistant professor at CDISE Skoltech. And this talk was prepared together with Anna Butorina and Alexey Kuzmichov, who represents here the Russian Quantum Center. So this talk will be devoted. We started to work. I'm sorry, I will introduce ourselves. We started to work with MEG only about 2 years maybe ago, and we were newbies there, and I consider myself to be a newbie right now in the MEG area, because this area is extremely complicated and extremely interesting actually. And this talk will be devoted to MEG, its evolution and trends. The first part of this talk will be devoted to a very short, a very brief review of the state of the art of MEG today. And then I will proceed to the description of a new solid-state sensor, which feasibility in terms of MEG has been proven by us in this year. Here on this slide, you can see the map. Actually, this is not the map of MEG. It is the map which I took from the site of, from the brochure of YIGM magnetically shielded rooms distribution. This map shows where the magnetically shielded rooms with the highest magnetic shielding coefficients are installed. And since most of these rooms are related to MEG, so this map may give us some idea on the distribution of MEG all over the world. We can see that most of MEG setups are located in the countries of Europe and North America. Some MEG setups, or at least YIGM magnetically shielded rooms, are installed in China and in Japan also. In Russia, we have actually 2 magnetically shielded rooms by YIGM. The first one is installed in Moscow MEG Center, and the second one is installed in the Russian Quantum Center. And to the date, currently, most of MEG systems are based on superconductive quantum interferometers, or briefly SQUIDs. And for brevity, I will refer the systems as SQUID-MEG. These systems, as you know, are rather expensive. Unfortunately, they use low temperature superconductivity, I mean the conventional SQUID-MEG systems, of course. And due to need of liquid helium, supporting of these devices is also very expensive. I mean, supporting in the working state. This leads to unpopularity, unfortunately, of the MEG. MEG is, I think, the most informative non-invasive tool for neuroimaging. However, due to due to high prices, this method is still unpopular. This method is relatively popular in Europe and in North America. However, in Russia, for example, we have only one MEG setup. But the interest to MEG increasing dramatically since 2017, because in 2017 the world market meets the optically pumped magnetometers. This is a new kind of magnetometers which are high sensitive and may solve some problems of conventional MEG systems. We will talk a bit later about it. Right now, OP-MEG or OPM-MEG systems became kind of well-established approach to MEG, and there are various teams all over the world which are building these MEG systems and using this MEG systems at least for academic, for research purposes. Also, at Skoltech, we also make our own prototype of OPM-MEG system, but this is the present. And now let's talk about maybe future, like I don't know, science fiction. During the previous year, 2 promising MEG feasible sensors were developed in Russia. The first one is non-zero field OPM, which is being developed by EOF Institute together with the Higher School of Economics. I don't know, Alexey Asachi is here, Professor? Oh, unfortunately, I don't see here, but EOF Institute together in collaboration with Alexey Asachi also now successfully researches the area of OPM, and moreover, these OPMs may be even better than the OPMs shared on the market at the moment. And the second sensor is a solid-state flux-gate magnetometer, which has been developed in Russian Quantum Center. And I will not stop in details on this slide about this magnetometer, because we will talk about this magnetometer in details later during this presentation. Thus, we have like 3 whales of EEG, of MEG, I'm sorry. So first of all, it is a SQUID-based MEG. Then it's atomic magnetic measurements or optically pumped magnetometers, and OP-MEG or OPM-MEG. And also a new kind of magnetometer, a solid-state flux-gate magnetometer, which I will refer as YIGM, or just YIGM if we talk only about the magnetometer. Looking at the history of the magnetoencephalography, we need to remember that magnetoencephalography has been, that the first SQUID sensor has been proposed by Jim Zimmerman in 1965, and the first application of this magnetometer, of this new at that time magnetometer to the MEG area, we can see that it was done by David Cohen and Edgar Edelsack in 1971, 50 years ago. Nowadays, we have several brands which are producing the MEG systems, the SQUID-based conventional MEG systems. And we can conclude that this technique is very, very well established, and it's actually brilliant devices made by NeuroMag, by Elekta, and by CTF. They have a lot of a huge number of channels, and this huge number of channels allows to use like signal space separation very effectively. But this conventional SQUID-based system, unfortunately, have some problems. And I think you know these problems. First of all, it's a need for liquid helium, which leads to a very high OPEX and CAPEX. Then large source to sensor distance, because these sensors should be cooled with the liquid helium, and they cannot be placed in conventional way to the scalp, right to the scalp. Need for liquid cooling also leads to non-adaptable sensor arrays. I mean that we are unable to adapt the helmet to different sizes or shapes of the head. And of course, large size of the setup of the system. Well, large size of the system is not a problem actually of the system itself, but the problem is that for this large size, for these big systems, we need a big magnetically shielded room. And magnetically shielded room by vacuum schmelze have a huge weight. It's about from 8 to 10,000 kilograms, and they are extremely expensive. The price of vacuum schmelze magnetically shielded room varies from 700,000 to $1 million US dollars. So all these problems unfortunately lead to low popularity of MEG systems, and this low popularity consequently leads to only a small number of the laboratories all around the world can use MEG actually, and even in order to build the list of applications of MEG in clinics or in just researches, we need to increase the popularity of MEG. We need to increase the number of researchers which use MEG technique. And some of these problems actually for SQUID-based MEG may be effectively solved. And I think Professor Justin knows how. I'm talking first of all about the High-Tc SQUIDs. These setups, first of all, these sensors use not the helium but nitrogen. Nitrogen is much cheaper than helium, and thus usage of nitrogen solves the question of high price, partially, of course. Then these sensors can be placed right on the scalp. The scalp to sensor distance may be reduced up to 3 millimeters, while actual for MEG systems distance is about 3 centimeters or 2.5 or 3 centimeters, which is 10 times higher. Of course, this reduced scalp to sensor distance leads to much higher signal to noise ratios of MEG systems, which are based on High-Tc SQUIDs. Taking into account low intrinsic noise, we can assume a great SNR, which leads to a good resolution, and even we do not need a big number of sensors in order to obtain the resolution which is comparable to conventional SQUID-MEG systems. However, the systems are also rather big, unfortunately, yet. Another direction which assumably may solve some of issues of conventional SQUID MEG systems are optically pumped magnetometers or atomic magnetometers. Nowadays, as I said before, there are several university teams or even companies which are producing the sensors like Q-spin or even commercial OP-MEG systems like Circa or Fieldline. Also, I would like to highlight this very beautiful project, kernel, which actually on the site, or if you will open the site of kernel, you will find there even OP-MEG system, which includes more than 700 channels. I don't know about commercialization. I don't know about the prices. I can only suspect that price is rather high. However, of course, the resolution of this system is also very high. now, during the last maybe 5 years, there are a lot of researchers which can give us some hints about the OP-MEG future. First of all, several independent teams are now working on development of optically pumped magnetometers of high sensitive optically pumped magnetometers, which can work in unshielded environment. I mean, without any magnetic shields. Of course, it's like science fiction right now. As for me, I'm unable to imagine now unshielded MEG, not because of sensors, but just because of weakness of the magnetic fields produced by brain and huge amplitudes of magnetic noises, of ambient magnetic noises. However, theoretically, it's possible, especially if you will come far away from cities. And now, for example, in UFE Institute in 2021, in this year, UFE Institute, together with Alexey Asachi, presented also a new kind of magnetometer. You can find here the link to the paper. And this magnetometer also is very high sensitive. It demonstrates intrinsic noises about 13 femtoteslas divided by square root of hertz. So this might be a direction on the future of MEG, reduction of magnetic shielding, because magnetic shielding actually, if we now will take a look at the OP-MEG system itself, it will be much cheaper than the magnetically shielded room provided by vacuum schmelze. So another direction I would like to highlight is the helium-based optically pumped magnetometers. Actually, in my head, it could be related to High-Tc SQUIDs, because also it's a room temperature OPMs, which can be placed right on the scalp surface, right on the head. And of course, not only Levitt like here, but also Ivanainen, Tim Tierney, and Samuelson shown that for this magnetometer, we can increase the signal power up to 7.5 times. So this might be also a very prospective direction to develop optically pumped magnetometers. Here you can see a very simple table which shows the main characteristics, including prices, of 3 considered MEG kinds. And of course, firstly, we need to look at the CAPEX and OPEX. It's the prices, so operation and capital. And we can see that the prices are 10 to 100 times lower than for conventional SQUID MEG system. For OPM, if we are talking about OPMs, which are presented on the market right now, it's Q-spin, for example, OPMs. These OPMs use zero field resonance, and for these OPMs, we need to use magnetically shielded room or at least magnetic screen with a very big, with a very high coefficients of shielding. However, we need to understand that these OP-MEG systems are compact, so we do not need such a big MSRs produced by vacuum schmelze, and these MSRs can be much cheaper, 10 times cheaper, for example, if we will make it much smaller. Then we will talk later about YIGM MEG, and here it's also kind of science fiction, because as I said before, we need very precise mathematical algorithms in order to distinguish useful signal produced by brain from the magnetic ambient background. However, theoretically, potentially, these sensors, as you will see later, have a much higher dynamic range, much wider dynamic range. And so theoretically, they also do not need such strong magnetic shielding. And now I would like to jump to description of our sensor, first of all, of yttrium iron garnet magnetometer, or YIGM, and to the description of study of our research on feasibility of this magnetometer in terms of MEG. But first of all, I would like to give the word to Alexey Kuzmichev. Alexey is a research scientist at Russian Quantum Center, and he develops this sensor. So I think he can describe this sensor, physics of this sensor, and its characteristics in a much more professional way than I can. Alexey, are you here?
Yes. Hello. I'm very glad that Nikolay invited me to speak today for you here. And I would like to start from the very beginning of flux-gate magnetometers. It was developed actually a very long time ago, maybe a century or even more. People notice that if you make a simple coil from a wire and put a magnetic core inside, you can actually somehow influence the inductance of this coil with magnetization of the core. It was the basic idea of all flux-gate magnetometers, all of the types, and this is the main idea of our sensor also. But this approach proved to be not very good as it is, because if you are, as you can see here, make a magnetization reversal hysteresis on some big core, for example, iron, just a piece of iron, there you will find a threshold for your sensitivity because of back-hour effect. This effect occurs because of domains, magnetic domain system inside this core, which is not actually, magnetization is not repeatable. It will, magnetization reversal will be different every time you make it. So this is produced some noises. And the history of flux-gate magnetometers is about fighting these noises, noises of the magnetization reversal. And lots of different ideas was used. And now the best way, as soon as I know, is our approach. That is about making this reversal with the rotation of magnetization. The idea is that you are not actually going to the slope of the hysteresis. You are always in a saturated state, so you are making some kind of one big domain, and you just rotate this magnetization of this domain over the core of your system. And with this, you can hope to make a better sensitivity. And as you can see on this picture in the left corner of this slide, there are not just circle form of our core, which is on a photo. You can see these brown circles. It's not a flat circle. It's actually have some complicated geometry. It's some stepwise edges. This is this special form is also because we need to fight the production of noise domains in the structure. And the main idea of the sensor, main core element of the sensor is actually yttrium iron garnet. It's a very specific material. And our core is actually a flat film, only 10 micrometers wide, and it made by liquid phase epitaxy on a some substrate, which is actually you can see on photo. Then we just put some orthogonal coils above this core, and these coils also make external field, which is rotate, and with this field we rotate the magnetization of the core. And how actually we produce a signal, how we make the measurement of the external fields. While we make this reversal magnetization with external field, we have a uniform rotation, and when some external signal comes, it somehow ruins the uniformity of the rotation, and we can see different harmonics in this process in spectrum. And by these harmonics, we can actually recalculate this in some kind of magnitudes of field. And up to now, our best sensor sensitivity is 35 femtotesla divided by square hertz. As we know, it actually is the best possible sensitivity for flux-gate type of magnetometers for now. And if we want to compare the sensor with OP-MEG or SQUID, one of the main properties of our sensor that is much better than for SQUIDs and OP-MEGs is its solid state. Solid state is very important because if you want to move your sensor in space or make it work in some harsh environment, you need it to be solid, so your construction not expect any different in the properties during this process, so the external impact will not ruin your measurements. Wide dynamic range, it is also very important property if you want to be less shielded. So if you want to use some cheaper shielded rooms, or not to worry about zero fields or something like that, wide dynamic range is very helpful because the sensor can work actually not only on very low external fields like 35 femtotesla or even nanoteslas, but much higher. Working at room temperature also is very good because you do not need some special way to increase temperature like in most of OP-MEGs for the gas capsule, or lower the temperature like in SQUIDs. you can just operate in a temperature that it is in your room. And so heat dissipation, it's like following the working temperature, is very low for our sensor comparing to the Q-spin OPMs. It is actually about the comfort of measurement, because the subject, the person who is wearing your helmet with sensors, will expect less stress, because actually 700 milliwatts is pretty much, and it's actually pretty hot for your head to make a long measurement. No need to calibrate is every sensor actually need to be calibrated, but we mean here that we do not need to have a zero chamber or zero field, that we actually must calibrate this sensor in this field before we actually use it. The calibration for our sensor can be made before measurements automatically in any field, and then it will start the measurement in a common way. Tangential measurements, the minimum distance from the surface. This is due to the geometry of our sensors. It's actually a flat sensor. It's only half of the millimeter flat, half millimeter flat rectangular element with a side of this rectangle about 30 millimeters, 30 or 40 millimeters. And if we put this element, this flat side, to the source of our signal, the distance between the source and the sensitive element is actually a millimeter or two. It's a very low distance. And theoretical limit for our sensor is 1 femtotesla divided by square hertz. It's calculated and some calculated estimation of our sensitivity. It is due to optimization of this all construction, the sensitive element, the core, and some electronics that are actually pretty complicated for this type of sensor. And we can also decrease the size of this sensor drastically, and make its sensitivity better. We have some approaches for that, and also one of our efforts for this very promising is to change the sensitivity approach from actually coils to some optical one. The external field will still be rotating our core with coils, but the to read the actual magnetization of this core, we are going to use some laser or something like that, and we hope that this will help us to make the sensor compact and also increase its sensitivity. This will be one of our challenges for future year or two. So that's pretty much about the way our sensor operates. If you have some questions, I will be happy to answer.
I have a question, actually, two related questions. So you said rotation. What kind of rotation? Is mechanical rotation, and what's the frequency of rotation?
By rotation, I mean the rotation of the magnetic field. if you have two coils, like on the picture, if you make the current in these coils with some phase gap, yes, you can actually make a rotating field inside these coils. And this rotating field will saturate our core also, and this saturation will follow the field, and so you obtain some kind of magnetization reversal, but by the rotation, actually without go to the hysteresis slope.
And what's the frequency?
Right now, our frequencies is hundreds of kilohertz for this, but it's not a threshold. We will work about increasing this frequency to make our element smaller and to increase its sensitivity. We need to make higher frequencies, and to make higher frequencies, it is very crucial to have a low saturation field. And as it now for our sensor, the saturation field is about 5 Ersteds. It's pretty low.
Are they going to interfere if you have two sensors near one as the other? Will external field of one of them interfere with the other one?
Well, we made such a measurement, and as we noticed, the influence is very small, and it's so small that we actually didn't see any change in spectral noise spectral density of our sensors. And I believe as soon as this measurement is vectoral, we can easily extract this kind of interaction between different sensors to make pure signal from the source. It's not a complicated task.
Thank you. Very interesting, very promising. Thank you.
So, Alexei, thank you very much for your presentation. But we are not specialists, we are not physicists, of course. But what we understand very well that sensitivity is very important, of course. And your current sensitivity is 35 femtotesla, as you said, but theoretical limit is 1. And how practically possible to reach with theoretical limit? What would you say?
Well, there are different approaches, and now we are working on them. There are several ways. One of them is to increase the frequency of this magnetization reversal and improve the core. So now we have 10 micrometers of the film, actually, of E3 iron garnet film, but it can be bigger. And with increase of this film, we can increase the sensitivity. There are just some technical problems to make this film uniform. If it grows bigger, the bigger the film grows, the more complicated the way to make it uniform. And right now we are working, and I believe I saw the films. Now they are already produced, and they are 3 times wider than this one. And we will make new sensor with them. Right now it is not actually prepared. It just lay on in our safe, and we will try to make better sensitivity with it. And the other way to improve is to make the system using some lasers and optical approach. using magneto-optics effects in this core to sense its magnetic moment, and then it will, I hope, drastically shorten the size of the sensor, and also the sensitivity will improve.
So your expectation is that you will be able to reach sensitivity of conventional low TC system. Am I right?
Well, it's hard to predict the exact numbers that we will eventually have, but I think that there are a lot of room to improve right now. Okay. So it's not a state of art, the sensor right now.
Okay, thank you.
I would like also to make a comment that as far as I understand, Alexey, please correct me if I'm wrong. Right now, we are not sure on the nature of these high noises. I mean, these 35 femtoteslas. Because these noises can also be produced by electronics, by just infrastructure of the sensor, but not by the sensor. And now, as far as I understand, RQC team from Russian Quantum Center, is also preparing a new generation of these electronics.
Well, yeah, we working on that also. The new generation is now producing, and it's only just one way to improve, and we hope that we will simultaneously work on these 3 different approaches, and eventually, in the end, all of them will take a part in improving of this sensitivity, and it will be improved. I hope that in near year 2 we will make some serious progress in this.
I have several questions, but maybe if other people have questions first, they can go. I don't want to monopolize people's time.
No, great. Please ask your question, because I think you're one of the main specialists here.
One of the only.
Okay, so first I just want to say that I'm really impressed. This is actually very exciting to see, and I know how much work goes into this kind of thing, so I congratulate you for how far you come, because I think flux gates have always been sort of left to the side, and it's really impressive to see that you've managed to get them to the sensitivity levels that you show, but also to do some nice MEG recordings with them. So congratulations.
Oh, thank you.
And I don't by any mean these questions to be difficult. They're really just curiosity based. So I hope you can understand that. My first question is about bandwidth. So at least from what I can tell, you're doing a lock-in type measurement. And yeah, obviously the sensor bandwidth is one and the lock-in bandwidth is another. But if we just focus on the sensor bandwidth, how far do you think it can go?
You mean a dynamic range here? Or
no, this would be so the actual frequency range of the detection.
Frequency. Yeah. Okay. As it is now, we measured it from the 1 Hertz to 500 Hertz, and as we can see, the more we increase the frequency, actually, the better the performance of our sensor becomes. And there are no any obstacles that I can see here to increase the frequency. So it's actually, we have some deviance of this construction for some other projects also, and they also sensitive elements with some electronics and everything, something like this, but much more easier on a very low level of these electronics, I suppose. And there our frequencies we operate with this core is actually kilohertz, tens of kilohertz, and they are still working pretty nice. This approach is useful there. And if we at some time we would need the actual frequency to be measured, I see no obstacles to improve electronics and all our construction to actually achieve a great sensitivity of on any frequency.
Yeah, I mean, that's one of the nice things about this kind of technology, but it's similar with OPMs. You can change the operating frequency and therefore shift your sensitivity to different bands, let's say.
Yes, it's actually very similar to common flux-gate.
Right, yeah. But in relation to that, so the dynamic range you mentioned is some Ørsted, and I think it may be worth emphasizing how good that really is. I mean, compared, as you know, compared to OPMs, that is actually a very wide dynamic range. And,
it's very wide. It's actually 3 orders of magnitude.
Right. Yeah. So I think that's something impressive, and that's something that many people maybe don't quite follow or understand clearly enough with OPMs until they start trying to use them for MEG, and they realize they need to cancel the ambient field, and they're even within an MSR, etc. So I think you should emphasize that more clearly.
Yeah. I can also add to this that we with Nikolay, we collaborate on these measurements, and we actually tried we also performed some measurement using OPM, and during my experience, and I think Nikolay will agree with me, to actually use OPM sensors is much more harder than use this one. It have
yes, I agree.
better sensitivity. Yes, OPM right now is more sensitive, but the way of using it is very complicated, and it's very hard actually. And with our sensors, we actually made measurements in a very easy way, in a way you actually imagine the measurements. Yes, you just put the sensor, push the button, and you have your measurement, quite like this, without any troubles.
Right. Yes, I am also aware of the challenge in using OPMs. Yes. On a very different topic, but related to sensitivity, I also am curious about, you were mentioning the squeezing the size of the sensors. And there, I think it's important to keep in mind that you're essentially integrating the field over the plane of that sensor. And when you're doing, for example, normal field measurement, so measurement of the magnetic field, neuromagnetic field that is normal to the surface of the head, then your sort of integration area is rather large, and that means that you're sensing from a higher distance from the head. That's obviously not an issue per se, but I think it's worth considering pushing the size down of the discs. As you mentioned, I think that's something you're looking into anyway, but that certainly has an impact on the let's say, sensitivity to, or to put it another way, the closer all of your sensor is to the head, the bigger the signals are, right? So the signals are falling as a function of distance, and if you're integrating over a large area that is, the center of mass, let's say, is some distance from the head, then you're losing some signal, let's say.
Yes, it's just actually a very good comment. We made this size of our sensors just because it's easier to operate with it when it's quite large. And as soon as these measurements are some kind of pioneer measurements, we use this geometry. But in future, of course, we would like to make it smaller. And we are working on this, and we hope this will in the end improve sensitivity also in MEG measurements. So it's a kind of crucial moment that we actually, yes, we integrate the signal over all our core and this will affect our sensitivity in MEG, because the head is actually not flat. Yes, it's some kind of sphere, and the smaller we have the sensor, the better, the more accurate we can position it to measure some something.
I'm sorry, I'm afraid that I didn't understand, and maybe the question, because I think Justin meant that small size of the sensor do not allow to see brain activity very well, because you see...
that was not what I meant.
No,
So
okay.
He answered my question well, and I mean essentially what I'm talking about is the sensors that they have now. They're constructed like this, more or less. So the average sensitive point is, you know, sort of the middle of that disk. So the smaller you make the sensor, the closer the average area is to the head surface, and therefore the larger the fields.
By the way, I will also make some comments during further presentation on this question, on this issue. Colleague, do you have other questions, or can I proceed?
Go ahead, please.
Okay. So now I would like to describe our research on the feasibility of the sensor, and maybe make some comments on the size of the sensors and all these questions. One moment. First of all, we of course started with the empty room study and with the sensor calibration. The sensor calibration is very simple, actually. We just put the sensor inside the coil with a known magnetic field at the center of this coil, and just calibrated it once. Then we started to measure the background noise in an empty MSR. And during these measurements, we obtained the mean noise spectral density for YIGM sensor. It was about 35 femtoteslas divided by square root hertz. However, we obtained also the intrinsic noise for OP-MEG, not the intrinsic noise, of course, but the noise floor, about 30 femtoteslas divided by square root hertz. And that's why we decided to put these sensors, both OP-MEG and YIGM, inside additional permalloy tube. And there we measured for OP-MEGs the sensitivity, which is declared by QSpin company, which is about 10 femtoteslas by square root of hertz, and the same 35 femtoteslas for YIGM. And these measurements allowed us to assume that these 35 femtoteslas by square root of hertz is the intrinsic noise of our YIGM sensor at the moment. After that, our feasibility research was devoted to registration of the algorithm. We registered algorithm in 3 healthy adult subjects, and for each subject, we first of all conducted OP-MEG experiment in order to find the hotspot, the area in which we can register maximum magnetic field produced by the algorithm. After that, we aligned the position of subject in order to put the sensor, the YIGM sensor, in this hotspot, and repeated the measurement. Both using OP-MEGs and YIGMs, we measured both radial and tangential components of magnetic field. Here on this slide, at the right hand side of the slide, we can see two schemes of positioning of the YIGM sensor for measuring the
radial and tangential components of magnetic field. And of course, if we will take a look at the distances, then for YIGM, then for radial measurements, the YIGM to scalp distance was about 1.5 centimeters, 1.5 centimeters. While for tangential component measurements, this distance was about half centimeter. And taking into account that for OP-MEGs, we just measure the distance between the center of the sensitive element to the scalp, then the distance is independent on the component we are measuring. So for OP-MEG, we set OP-MEG to scalp distance to be about 1 centimeter for both tangential and normal component measurements. And we obtained actually at the left-hand side of the slide, you can see the graphs, the spectra, so the signal, and we obtained very expected results. For measurements of normal component, the amplitudes are comparable when measuring with YIGM or with OP-MEG, but OP-MEG's signals are a bit more pronounced. While for tangential component, we have just reverted situation. The YIGM's signal when we providing tangential measurements are a bit more pronounced, but actually they are comparable. They're almost equal.
Excuse me, Nikolay.
Yeah.
On this slide, what is blue and what is red on your picture?
Yeah, I'm sorry.
Your spectra.
The blue line represents closed ice subject state. So the experiment on registration of the algorithm was conducted during 1 minute, and the first 30 seconds subjects were asked just to sit with open eyes, and after that he or she was asked to close his or her eyes. So the blue line represents just the spectra of the signal obtained with the closed eyes, while the red or orange line represents the open eye state. After that, we just applied bandwidth filtering to the signal just in order to obtain beautiful pictures. In fact, here you can see the tangential component for all 3 subjects. For it's the YIGM measurements. And concluding this part of my talk, I can say that after half of a century, we just repeated actually the work of Cohen of 1971 year. And of course, I can say that it is just the initial research, not more. So we are unable, unfortunately, to say that we have now a YIGM MEG system. We just have one magnetometer, which we hope we've proven its feasibility for MEG. But now it opens a wide range of future researches, which will allow us, hopefully, to construct multi-channel YIG MEG system. First of all, it is the research that we are conducting right now. It's the simulation studies. As Alexey said before, we can, for example, increase the pumping frequency, the remagnetization frequency, in order to decrease the size or increase the sensitivity, or proportionally decrease the size and increase sensitivity. So we need now some direction in which we should develop the sensors. And we now trying to build the research on simulation studies, which were inspired by works of Eva Nainin, of Tim Turney, of Samuelson. And it is, first of all, the lead field-based matrix analysis. We are building the lead field matrices for different positions, for different locations of sensors, taking into account actual or maybe future intrinsic noise of the sensors, and trying to understand which number of channels we need to obtain a good signal-to-noise ratio of the system. Then we also modeling task-oriented sources. Well, for example, if you remember, I was talking about this kernel system with the 700 channels. This system is brilliant. However, this is I suspect that this is very expensive. So we are trying to. We are now considering the possibility of building a low channel system. I mean the system with a low number of channels. And taking into account that, unlike SQUID, we can change the positions of the sensors. We can just make a lot of layouts, task-oriented layouts, which will provide us with a good spatial resolution of source localization in just the area of interest. We are now trying to also to do this, and for this we are now just modeling a lot of. Also, we are exploring now the spatial resolution of of source localization or of the solution of the inverse problem with the standard methods, and of course we need to develop our own methods, because it's well, what is the motivation? For example, yeah, I have here the example. The YIGM sensor is flat and can be placed directly on the scalp for tangential component measurements. However, it's well-known fact that we have a high, that the tangential component of the magnetic field is the subject for high impact of volumetric currents. So we now need to improve methods of localization, and maybe make the localization methods on the basis of tangential measurements. And we have some ideas on it, but the ideas are not checked yet, at least. And I will be happy, of course, to tell you about these ideas in future. Also, what we need to do is we need to proceed one channel YIGM MEG studies. First of all, we need to develop a new generation of sensors. The technical process may allow us to increase sensitivity to reduce intrinsic noises. We need, of course, to provide accurate comparison with OP-MEGs, with SQUIDs, and of course, we need to catch some responses, maybe audio or visual or sensomotoric responses with our sensor. Also, we would like, it's our dream to catch the gamma rhythm. We unfortunately did not try to do it before. And we hope that all these researches will give us some ideas, some hints on how to make the multi-channel YIG MEG system. After, of course, accurate exploration of possible crosstalk effects, and we need to study the sensor positioning, but hopefully we will do it in maybe a year or two, because now YIG sensors are in production. So I think that by the end of this year we will have already sensors in order to construct like 10-channel system maybe. So this is the end of this presentation, and thank you for your attention. I will be happy to answer any questions, and we are open for any discussion.
Well, Nikolay, thank you very much for your very interesting and exciting presentation. And of course, it would be great to see some prototype of working system in, as you said, already 1 year, and try to record gamma rhythm with this. But do you expect sensitivity be better at that time, or?
Yes, we expect sensitivity to be better. We don't know which sensitivity we will obtain. However, we are working on it right now, and I hope that we will at least have a 20 femtoteslas or even 15 femtoteslas. Of course, not the theoretical limit in 1 femtotesla. It's not for 1 year.
Related to that question,
so
how reproducible?
Another question.
No, I just wanted to ask about the reproducibility of the sensitivity. Is it every sensor gets roughly the same sensitivity, or do you have to make 10 to get that sensitivity, or 100, or?
It is. It's a very good question, and I'm also curious about it actually.
I can actually answer maybe on this. Of course, it is not like we make only one, and we actually try to make a lot of them, and 35 is actually the best we actually made, but it is 35 to 40, so they are quite repeatable, and I believe it is. It's not a problem to make the process of creating this sensor good, because there are, for example, I think six of them right now in our possession that are near 40 femtoteslas, and it's not also bad, I think.
As far as I understand, the sensitivity of the sensor depends also on a quite precise lithography in garnet, and these sensors to the moment are made like on the knee, you know. so we hope that the fabrication process will be improved, and will consequently improve the sensitivity.
So may I ask about sensitivity? Is it the same across a wide frequency range, or is it worse or better for some frequencies?
Let me please return to this slide. Here you can see only from 1, actually not 0. It's an error, from 1 to 130 hertz. But at least here you can see that sensitivity is almost the same.
Okay, so should we look at the first picture? Yes.
Yes, we can look at all 3 pictures. The red curve represents the YIGM sensor at all 3 pictures.
Okay, thank you.
So I think crosstalk is something you've touched upon, but I'm curious about sort of the proximity you had between the sensors when you indicated that the crosstalk was very low. For us, at least, with coils that are roughly the same size as yours, so something like a centimeter or so, when we place them, you know, right next to each other, the crosstalk is quite big. So I would imagine that if you bring two of your sensors, let's say if they're both oriented parallel to one another, then the crosstalk will not be so negligible, or?
This is the thing that we need to study, because right now we have only one, the sensor. I can say, or maybe Alexey can say about the magnetocardiography setup, because the team of Russian Quantum Center combined the sensor in the array, sensors in the array, but I'm unable to talk about the distance between the sensors. Alexey.
Yeah, I can comment on this. Actually, when we studied this sensor development, the first idea we had is to use it in magnetic cardiography. The signals of the heart is larger than of the brain, and we had at that times we had not that good sensitivity, so we tried to create some magnetocardiographic device, and to do so we combined three sensors. We make some kind of lineup of three sensors side to side, and make the measurements moving these sensors across the chest of some human, and there was actually no problem at all with some crosstalks. We do not measure it we do not have some purpose of measuring these crosstalks. Maybe in some configuration there will be some significant influence, but in just line up side to side, there was actually zero crosstalks, as we could see on our spectrum. So I believe it's pretty closed loop system. The field inside the coil, the biggest field is inside the coil, and outside of it, very fast decay of the magnitude of the field, and when it gets to the core of the next sensitive element, it could be 3 or 4 orders of magnitude lower than it actually inside the coil. So the influence is negligible, I think.
But what was the distance between the sensors in magnetic cardio?
Well, we put it just side to side. I believe it was a few millimeters, like 5 millimeters maybe, between sensors, and it still was okay. So
yeah, so I can just comment that I mean that works, I think, perfectly well for those kinds of spacings. But Nikolay raises an important issue, and I think it's also something that should be kept in mind. So the distance, let's say, between the outer edges of the sensor is one thing. It's the distances between the sensing or the center of the sensing element that's important for MEG. And there, depending on the layout, Nikolay, as you're digging into those kinds of calculations, you're going to find that that spacing is very important. And when you're on scalp, most, let's say, the rule of thumb is something like you're going to want to have a sensor every 5 millimeters. And with those kinds of spacings and sort of the geometric sizes of your samples, I think you are going to have crosstalk that's on the order of, yeah, maybe 5 to 10%. And that is, as you mentioned, can be accounted for in, let's say, post-signal processing, but the second order terms are going to be non-negligible as well, and those are much more difficult to treat. And yeah, so I mean, long story short, I think crosstalk is something you're going to need to dig into a bit. It's not generally a problem for MCG because you don't need such dense spatial sampling, but if you really want to take advantage of coming closer to the scalp and try to push the resolution limits of MEG, which is where I think one needs to go with on-scalp MEG, then you're going to need to be dense sampling with a very dense array, so 5 millimeters or so between them.
Yes, I fully agree. And of course, there are there are now well, this study opened a lot of problems actually, and this is one of them. So of course we need the study. Of course we need to study accurately the possible crosstalks, and when we decrease the size of the sensors, of course this crosstalk might increase. So we'll see.
So I can also maybe comment, I know, and I've been through the challenges you've also indicated regarding trying to indicate that you can get better spatial resolution or even to investigate the resolution limits. So Nikolay, you're welcome to email me. I can hopefully provide some useful tips on approaches. I think in general, going to inverse methods is can be revealing, but is also very difficult, first and foremost, because as you said, if you're going to be measuring tangential magnetic components, then you also need to account for the return currents, which is very difficult. But also because of the fact that any inverse model has a lot of assumptions in it. And I mean, Elena can tell you all about those, or other colleagues working in MEG can tell you about the assumptions in many of those models. And for investigating something like we physicists like to do, like spatial resolution, those kinds of assumptions can get quite annoying.
Yes, thank you very much. Actually, it's even would be a good idea to make one more seminar on the solution of the inverse problem. It's actually very interesting to me because I'm not a physicist, I'm a mathematician mostly. So now I stacked a bit without physical problems, but I hope to return to mathematics one time. And then I hope that I will be able to, well, you know, I have some interesting ideas. For example, how to, I mean, ideas on how to neglect the influence of the volumetric currents. I mean, how to count this influence. But I need, of course, to check these ideas, and I'll be happy to discuss maybe these ideas. Maybe these ideas are not subject to be checked. I don't know.
Okay, so Nikolay, thank you very much. Once more, do we have any other questions? No?
It's a good idea to meet again on the inverse problem. Have another seminar, so maybe we'll have to discuss that.
Boris, I'm sorry, I have a problem with my headphones, and I was unable to hear you. Could you please repeat?
I mean, that was a good idea to have another seminar to discuss the solution of the inverse problem.
One moment, I'm still not able to hear you. One moment.
Does anybody hear me?
Yes, we hear you.
Okay.
Yes, sir.
So anyway, we can discuss
Okay.
that. We can discuss that via email. I meant that we could have another seminar concerning the solution of the inverse problem, since it's interesting for, I think, all of us. And many of you are indeed developing it, so it might be really interesting.
Yes, I fully agree. I fully agree. And, yeah.
Okay. And thank you. It was really interesting, and it's just new something. Quite exciting. So good luck. So have. We wish you further success with this.
Thank you very much. We will we will be on contact, and so maybe Actually, I'm open to such seminars. It's very interesting to me, and I would like to be a part of society, not only just alone Nikolay Koshev. So
Good,
thank you very
good.
much for this possibility.
Good. Okay, thank you.
Thank you.
So goodbye.
Thank you.
Goodbye.
Thank you. Goodbye.